Greetings everyone. My name is Anand Dubey and I am currently pursuing my degree in civil engineering at the Faculty of Engineering and Technology, University of Lucknow. Today I am excited to present you an in-depth seminar on the new Austrian tunneling method, commonly known as NATM. Moving on to the content of the presentation, the aim is to provide an overview of NATM, history, its principle, psychology, and why NATM is necessary, its execution process, and its application in real-world project. Lastly, some references. History of NATM. The term "anatium" originated in Salzburg, Austria. Austrian engineering traditions and post-World War II reconstruction needs laid the groundwork for anatium in between the 1920s and 1940s. It was first used by Ludwig von Rapsewicz in 1962 and gained worldwide recognition in 1964. The first use of anatium in soft ground tunnel was in Frankfurt metros in 1969. The basic aim of anatium is to achieve a stable and economic tunnel support system. Introduction about anatium. Anatium is an innovative tunneling technique that leverages the natural geographic strength of the surrounding rock to support the tunnel structure. It is also known as the sprayed concrete lining, in short, SCL method, which uses sprayed concrete shotcrete to provide immediate support to the tunnel walls right after excavation. This method focuses on minimum use of heavy support structures and instead utilizes the inherent stability of the rock mass. Let's discuss some important principles of NAT. The first principle is mobilization of rock mass strength. This method relies on the inherent strength of the rock mass being conserved as the main component of the tunnel support. The second principle is shotcrete protection. Applying a layer of 25 to 50 mm of sealing shotcrete immediately after opening the face to minimize loosening and excessive rock mass deformation. The third principle is measurement. In this, sophisticated measurement instruments are installed to monitor every deformation of the excavation. Last, fourth one is primary lining. In this, a thin active support system using a flexible combination of rock bolt, wire mesh, and lattice girders are used. The fifth principle is closing of inward. Early closing of the inward is done to complete the arc action and create a load-bearing ring, which is crucial in soft ground tunnels. The sixth one is rock mass classification. Expert geologists classify the rock mass during excavation to determine the primary support and further design support. Lastly, and the seventh important principle is dynamic design. And the design is dynamic during tunnel construction, with support selected based on rock classification and reinforced based on observed deformation. Let's discuss the psychology behind NATM. It emphasizes a design as you go and a design as you monitor approach, optimizing support based on observed ground conditions and convergence or divergence in the lining. Why NATM should be used? This is because it offers flexibility in excavation, geometries, and large cross sections, easy installation of additional support measures, cost effectiveness compared to tunnel boring machines, and easy installation of waterproof membranes and primary support. This slide contains sequence of important steps which are involved in the execution of NATM during the tunnel construction. These steps are portal development, survey and profile making, drilling hole and rock bolting, loading explosives, charging up to 20 to 30 minutes, blasting, defuming through ventilation pipe, removal of mud, scaling or chipping with help of broomer, first layer of shotcreting up to 50 mm, surveying, support system with the help of wire mesh, steel rib or lattice girders, second layer of shotcreting up to 150 to 200 mm, and lastly, systematic rock bolting. The following steps are discussed in detail in the upcoming slides. Portal development. This is the process of stabilizing the entrance and exit of the tunnel. It involves creating a secure and stable opening to ensure safe access for workers, equipment, and this step is crucial for the overall stability of the tunnel. Survey and profile making. The basic procedure of tunnel surveying is to analyze the center line of the ground and transfer that alignment to the tunnel. This involves marking the tunnel profile as per the design and drawing, ensuring that the excavation follows the planned path. Drilling hole and rock bolting. This steps involves making holes in the rock surface for blasting and rock bolting. Equipment like drill jumbo and crawler drill are used for this purpose. Rock bolts are inserted into these holes to stabilize the rock and prevent collapses. Loading explosives. Explosives are loaded into the drilled holes to break the rock. These are different types of explosives based on their chemical nature and availability, such as high or detonating explosives and low or deflagrating explosives. The choice of explosives depend on the specific requirement of the tunneling project. Charging. This involves preparing the explosive charges for blasting. The process includes placing the detonators and blasting cords in the drilled hole, ensuring that the charges are correctly positioned for effective blasting. Safety measures are strictly followed during these steps. Blasting. The process of breaking rocks into smaller pieces using explosives. Controlled blasting techniques are used to achieve the desired excavation volume while minimizing the impact on the surrounding environment. Proper permissions and licenses are required for the use, storage, and transportation of the explosive. Ventilation in tunnel, which is also known as diffusing through ventilation pipe. Ventilation is required to remove dust, gas, and smoke caused by drilling, blasting, loading of excavated materials, and shotcreting. It ensures a safe working environment by exhausting harmful gases and maintaining proper air quality. Phase mapping. After the blast, geological mapping of excavated phase are being done with their orientation, the geological features, including joints, faults, and faults with respect to tunnel, etc. is prepared. Based on geological observation, support system is decided and support is being installed. Mucking. Mucking is the process of removing the broken rock, which is also known as muck, from the tunnel after blasting. Dump trucks are used to transport the muck outside the tunnel. This step is essential to clear the tunnel for further excavation and support installation. Scaling or chipping with boomers. Scaling or chipping involves removing loose rock from the tunnel, heading to make space for tunnel support. This is done using a boomer machine, which helps to remove any remaining muck and prepare the tunnel space for shotcreting. Rock mass classification. Rock mass classification is a system used to categorize the quality and characteristics of rock masses. It helps in understanding the behavior of rock masses and determining the necessary support for engineering projects like tunnel and slopes. The classifications involve evaluating various parameters such as rock quality, discontinuities, and groundwater conditions. Rock Quality Designation Index, in short RQD. The Rock Quality Designation Index provides a quantitative estimate of rock mass quality from drill core logs. It is defined as the percentage of intact core pieces longer than 100 mm in total length of core. RMR value or rock mass rating. The rock mass rating system developed by BNSK utilizes six parameters to classify rock masses. The first parameter is uniaxial compressive strength of rock material, rock quality designation, spacing of discontinuities, condition of discontinuities, groundwater conditions, and orientation of discontinuation. Each parameter is assigned a rating, and the sum of these ratings give the RMR value, which indicates the overall quality of the rock masses. Q factor. The Q system, developed by Norwegian Geotechnical Institute, is another rock mass classification system that uses five parameters to estimate tunnel support. The first parameter is block size, interblock shear, active stress, reduction of joint water flow, and lastly, the fifth one is presence of weakness zones. Q factor varies from zero point zero 0.01 to 1000, from exceptionally poor rock to exceptionally good rock. Shortcut. Shortcut is a generic name for cement, sand, and fine aggregate concretes which are applied pneumatically and compacted dynamically under high velocity. Pre-shortcut. Pre-shortcutting. It is also known as the shortcut application during the first layer. The first layer of shotcrete, which is also known as speed concrete, is applied to the tunnel walls to provide immediate support. This layer is typically up to 50 mm thick and helps to stabilize the rock and prevent further loosening. Types of shotcrete. There are basically two types of shotcrete: dry mix shotcrete, wet mix shotcrete. Wet mix shotcrete, less power input is required and it has low initial cost. Also, the maintenance is low, productivity is completely low, and rebound is greater in this case. Wet mix concrete, in case of wet mix concrete, greater power is required. It is a costlier process, higher productivity, about 10 to 16 cubic per hour, causing less rebound. Tunnel support system. Additional support measures such as wire mesh, steel ribs, or lattice girders are installed to reinforce the tunnel structure. These supports helps to distribute the load and provide additional stability to the tunnel. Wire mesh. Wire mesh is used to support small pieces of loose rock or as a reinforcement for shotcrete, stabilization of applied shotcrete until setting and hardening. It also increases the shear strength, preventing dropping of shotcrete portion after cracking or failing of the lining. The standard size for wire mesh is 150 into 150 into 6 mm. Rock bolting. Rock bolts are systematically installed to further stabilize the tunnel. These bolts are inserted at an inclined angle into the rock and helps to transfer the load from unstable exterior to the stronger interior of the rock mass. Second layer of the shotcreting. A second layer of shotcrete, typically 150 to 200 mm thick, is applied over the initial layer and the support system. This layer provides an additional strength and protection to the tunnel walls, ensuring long-term stability. Tunnel lining and pavement. Lining in tunnel and pavement construction involve following steps. Fixing of reinforcement or waterproofing membrane. In this, a waterproofing membrane is installed to prevent water ingress. Erection of concrete lining gantry. In this, the gantry is a lead which ensures the concrete is poured uniformly and accurately. Concreting in tunnel. In this, the concrete is then compacted and allowed to set, forming the tunnel lining, GSB, which stands for granular subbase. In this layer provides a stable foundation for the pavement. DLC laying in invert. DLC stands for dry lean concrete. In this layer acts as a base for the pavement and provides additional stability. PQC. PQC is known as pavement quality concrete. This layer forms the actual pavement surface, providing a durable and smooth finish. Concept of the 3D monitoring. 3D monitoring is a new technique used for taking the right alignment of the funnel. Optical targets are used for determining the coordinates for measurement. The coordinates should be checked daily. It is necessary for the tunnel as by it we know any displacement and wrong alignment. Points to carry out a successful NATM process. To carry out a successful NATM process, following points should be considered. Understand the geological conditions and rock mechanics. Choose a tunnel profile that suits the geological conditions. Use flexible support system and cylinder linings to accommodate rock movements. Perform excavation with precision to avoid overbreaks. Avoid loosening and overbreaks to preserve the natural strength. Avoid Ensure direct contact between the rock or soil and the support system. Implement continuous monitoring and geotechnical measurement to assess the tunnel stability. Install support systems promptly and in the current sequence. Now, an in-depth analysis of the project to understand its complexities and implementation in the real-world scenarios. Case study 1. Mumbai Coastal Road Tunnel. Project details: location Mumbai, year 2019 to 2023. Tunnel length is 2.07 km. Geology: basalt, andesite, and laterite rocks. Client: MCGM. Contractor is HCC. Consultant is AECOM. And the cost of construction is rupees 1502 crore. NATM implementation: cyclic excavation and support to ensure stability. Semi-mechanized tunneling with a road header for efficient excavation. Rock bolts to reinforce the tunnel structure. Shotcrete for immediate support. And fiber reinforced polymer for tunnel structural integrity. Challenges faced: the tunnel had to navigate through varying rock types. Managing water ingress was crucial. Soft clay and sand posed significant challenges. Ensuring minimum environmental impact was a priority. Innovative solutions: precast concrete segments improved construction quality. Advanced waterproofing system prevented water ingress effectively. Advanced drainage system managed water efficiently. Digital twin technology were used for real-time monitoring. Benefits: it reduces construction time, completed in 4 years, achieved 15% saving, cut down 30,000 tons of carbon dioxide per year, designed for a 100-year lifespan. Awards and recognition: Best Tunnel Project at the 2022 India Infrastructure Awards, Excellence in Tunneling at the 2022 Construction Work Week Awards. Case study 2. Oslo City Tunnel. OCT. Project details: location was in Oslo, Norway, year 2016 to 2022. Tunnel length is 18.5 km. Geology: complex rock formations. Client was Norwegian Public Road Administration. Contractor Sakansa Norway. Consulted Norconsult. Cost was 12.5 billion Norwegian currency. NATM implementation: full face excavation employed for efficient tunneling. Mechanized tunneling using advanced tunnel boring machines. Rock bolts installed at 2 to 3 meter spacing. Shotcrete applied in layers of 50 to 100 mm. Steel arches installed every 1 to 2 meter for additional support. Challenges faced: vibration control was essential to minimize the impact on the surrounding structure. Managed rock stress up to 40 megapascals. ensured minimal disruptions to the city activities. The innovative solutions are advanced tunnel boring machines were used to enhance tunnel efficiency, real-time geotechnical monitoring improved safety and decision-making, automated short grid applications increases efficiency. Benefits: it reduces the construction time, achieve 12% savings, cut down 50,000 tons of carbon dioxide per year, designed for a 100-year lifespan. Award and recognition. Best Tunnel Project at the 2022 World Infrastructure Award, Excellence in Tunneling at the 2022 Construction Week Award. Following are the references used for the preparation of this presentation. Advanced Geotechnical Investigation for NATM by D. Columbus. NATM, a review of the current state of the art by J. O. Bickel. Oslo City Tunnel, NATM case study by T. O. Hogos. The new Austrian Tunneling Method, NATM, Principles and Experiences by D. Columbus. Tunneling Construction Challenges on Mumbai Coastal Road Project by B. Surana. Thank you everyone for listening.